This is the brief on coupled mass dynamics and orbital equilibrium. So this is a classic mechanics problem, you know? It's all about figuring out how the initial balance of forces between two connected masses basically dictates the system's entire future. Just picture a mass spinning on a table, right? It's tied to a string that goes through a hole, and on the other end, a second mass is just hanging there, providing tension. The real question is, how do you get that outward spinning force to perfectly match the inward pull from that hanging weight? Okay, so our first takeaway is force equilibrium. See, the system's fate is pretty much locked in from the get-go. It all comes down to whether that outward centrifugal force from the spinning can perfectly balance the inward tension from the hanging weight. So our second point is that this setup leads to three totally different outcomes. First, what if the initial angular velocity is too low? Well, there's not enough outward force, the tension from the hanging mass just takes over, pulls the other mass inward, and the whole system collapses. Second, what if the velocity is too high? Now, the centrifugal force is way too strong. It flings the mass outward, and you get this wild, continuous oscillation where it just keeps overshooting that perfect balance point. And finally, you get that perfect orbit. This is the sweet spot. It only happens when that initial outward force exactly cancels out the inward pull. So for our third takeaway, how do we describe this with math? Well, the key is to find what's called the generalized inertia tensor for the system. Think of it like the system's mathematical blueprint. It helps us predict all future motion, but only if we express it correctly using the system's coordinates, the radial distance and its angular position. So for these coupled systems, their final fate is really locked in from the start, all defined by that critical initial force equilibrium.